Welcome to this video, guys. We're going to review the multiplicative law of probability and the law of total probability. So let's begin. Let's remember the definition of conditional probability. The probability of A given B is just the probability of the intersection divided by the probability of the given event. How about if we solve for the probability of the intersection? Well, then we have something like this. Probability of A given B times probability of B. That's it. This is some authors say that there are two multiplicative laws when A and B are dependent and when A and B are independent. So according to them, this is the first one where A and B are dependent. So this is it. This is the multiplicative law. This law tells us how to compute probabilities of intersections using the conditional probability. So what happens if A and B are independent? Well, if A and B are independent, then this should happen. Let's focus on this term. Then the probability, the conditional probability, is just this. So if we substitute that in the probability of the intersection, we find that this is one of the conditions for independence, right? So there's a way to work out the independence conditions from the definition of conditional probability. How? Solving for the probability of the intersection and then assuming the independence, and that's it. So let's see a quick example. Let's work with an example. Assume that we have a box or a bag with 3 blue marbles, 2 red marbles, and 4 yellow marbles. Okay, so now we take one marble from the box, we record the color, and then take a second marble and then again record the color. So let's define two events. Let R be the event of having a red marble in the first drawing of the marbles, and let B be the event of having a blue marble in the second drawing of the marbles. So now I want to compute the probability that I will end up with a red marble followed by a blue marble, the probability of the intersection. So to compute this probability, we use the law, the multiplicative law of probability. So this is the probability of blue given red times the probability of red. This is just the definition of the multiplicative rule. So the probability of having a red marble in the first draw is just 2 out of 9, right? Since we have 2 marbles and all of them add up to 9, so 2 out of 9. And now we're going to compute this second probability. and to compute that probability we just need to realize that we have taken one of the 9 marbles. So now whatever this probability is going to be divided by 8 because we are missing the marble that we took here in this step, in the first step. R is the first step. So from the 8 marbles that are left, we want the probability of a blue. So since there are 3 blues, then we are almost done. We just have to multiply this times this. This is going to be 6 over 72, which is just the same as 1/12, and that's it. That's how we use the multiplicative law to compute probabilities of intersections. Well, now let's move on to the law of total probability. Law. There are a lot of laws in probability. So the law of total probability says, let me draw a Venn diagram. Let's draw omega. So this is omega, of course. Now let's draw some sets in any way that you want to draw them, but we have some conditions to fulfill. Let's say that this is, let's call these sets B1, B2, B3, 4, and 5. So these sets need to form a partition. We need a partition. So what is a partition? Well, a partition is just a collection of non-overlapping sets. Overlap, let me write it short. Overlapping sets such that their union is the sample space. So these non-overlapping sets make reference to this graphic idea of the Venn diagrams, of not having overlapping sets like when you draw something like this. So they are overlapping over here. So that's what we mean by overlapping in this graphical sense. And their union make omega. So we want a disjoint sets. Sorry, without this s, disjoint sets, and we want them, the union of these sets, to be omega. So here, this collection B1 and B2 all the way through B5, these sets form a partition of omega because they are non-overlapping and they cover all of omega. So now let's say that we have some set, some arbitrary set over here. Let's call it A. So this set A can be formed, let me write it, by this first piece. That piece is just A intersection with B3 union this little piece. That piece is A intersection with B2 union this little piece. That third piece is just the intersection of A and B1, and you're getting the idea. We have to get all the pieces of A in terms of their intersections with the partition B. And this last piece, which is before, let me write it over here. Union, the last one, A intersected with B4, right? B4 is this. So now we have found a way to write any event, the event A, in terms of the partition. So now we have a bunch of intersections, but this is the place where we remember the multiplicative law. Remember that the multiplicative law is this. The multiplicative law is just how to write intersections, well, probabilities of intersections, in terms of conditional probabilities. So now let's write this event A. Let me write it again very quickly. A was going to be A intersected with B1 and B2 and B3 all the way to B5. So the probability of A is going to be the probability of all these unions, but all these unions are disjoint, and we know that the union of disjoint events, the probability of the union, is just the sum of probabilities. So probability of A intersected with B2 and so on until B5. Okay, so now we use the multiplicative law and we transform the probabilities of intersections into products. So the probability of A is going to be the probability of A given B1 times B1, that times the probability of B1, sorry, plus the probability of A given B2. Remember, we are just using the multiplicative law. We're not doing anything new all the way until B5. And all these guys at the end, this is what we call the law of total probability. All this is a five partition, a set, a collection of 5 sets that make up this partition in this case. That's why we have 5 terms. So let's make a quick exercise using the law of total probability. So imagine that we have a factory, and that factory has 2 machines. Let's say machine 1 and machine 2. Machine 1 produces 60% of the factory's output, and machine 2 produces 40%. So machine 1 can produce defective or non-defective items. So let's say that the defectives produced by machine 1 are 4% of its production, and the defective items for the second machine is 5%. So let's say that we select one random item, whatever these machines produce, one random item. So let's say that we want to compute the probability of that selected item to be defective. So we want the probability of being defective. Well, using the law of total probability, in this case our partition are going to be the events produced by the first machine and produced by the second machine. So we have a partition because all the items are either produced by the first machine or the second, and they are non-overlapping events. Either the item is produced by machine 1 or by machine 2, but not by both. So according to the law of total probability, the probability of that item being defective is the probability of being defective given that it was produced by machine 1, let's write it like this, times the probability of having an item being produced by the first machine, plus the probability of being defective being produced by machine 2 times the probability of an item being produced by machine 2. So this is going to be the conditional probability, the probability of being defective given that it was produced by the first machine. So we know that it was produced by the first machine, so the probability of being defective given that it was produced by the first machine is just 4%. So we write 0.04 times the probability of being produced by the first machine is just 60% or 0.6. Again, this term is the probability of being defective given that it was produced by the second machine. So that's going to be just 5% times the probability of being produced by the second machine, 40%. This is, let me write it over here, something like this, plus 0.20, and this of course is 0.44 or something around 4.4%. So that's our probability of selecting one random item and that item being defective. So that's all for the law of total probability, guys. Thank you. See you later.